what's happening here? Do the circles shrink to 0? Here's another sequence. Again, regular polygons, but the number of sides doubles each time. This time, the circles don't seem to shrink to 0. Here's one last sequence. The number of sides of the polygons increases by 1 each time. Can you tell what the sequence of circles will shrink to? Each of those sequences made fascinating geometric patterns, and we'll see that the maths which is needed to answer each question is also interesting. In fact, that last case of triangle, circle, square, circle, and so on was first considered by the astronomer Kepler 400 years ago. The solution to that problem is quite hard, but you've already covered enough analysis to be able to answer the question, do the circles shrink to 0? Since the analysis is trickiest for this case, let's begin with the other two problems. First of all then, what can we say about how the radii shrink in this case? Triangle, circle, and so on.
Well, for this problem, we'll just have equilateral triangles and circles. And what we're going to show is that the scaling down factor is the same each time. You start with a circle here, where the radius is just 1. And its inscribed triangle, and its inscribed circle. In fact, all our three problems are going to start in this way. But what then is this next radius? Well, this internal angle is easy enough to find, because the angle from the center to the two vertices is 1/3 of 2 pi. That's because you've got a three-sided polygon. So this internal angle here must just be half of that, that is pi by 3. Now, consider this right-angled triangle. To find the length of this vertical side, we just use basic trigonometry. Now, this hypotenuse is of length 1. So this adjacent side must be 1 times cos pi by 3. So the radius of this second circle is cos pi by 3. And that's just a half. In other words, the next radius is half the previous radius. And you can see that exactly the same thing happens for the next triangle and circle. This length is just cos pi by 3. Look at this next right-angled triangle. Again, we have the same geometry as before, only scaled down. So the new vertical is going to be this hypotenuse, cos pi by 3, times cos pi by 3. That is cos squared pi by 3. Now, what will the nth term be? Well, the general term of the sequence becomes cos to the n pi by 3.
To determine what happens to the sequence as n tends to infinity is very easy. Cos pi by 3 is equal to a half. So that means that the sequence is a half squared, a half cubed, and in general, a half to the n. You might recognize it better as 1 over 2 to the n. And that's one of our basic null sequences, sequences that tend to 0 as n tends to infinity.
Remember, it was the analysis that proves that the radii tend to 0 in that case. Well, let's have a look at that sequence again. Notice that the radii of the circles continue to scale down by a half each time. That's why they tend to 0.
What about the second case then, when the number of sides doubles each time? Triangle, circle, hexagon, circle, dodecagon, and so on. What can Alan say about the sequence of radii?
Well, the starting point is the same. We've got an equilateral triangle, and this second circle, which we already know has radius cos pi by 3. how would you find this next radius? Well, this time we need to know the angle drawn between these two vertices. And for a six-sided figure, it's going to be 2 pi by 6. So this angle is going to be pi by 6. So this side becomes cos pi by 6 times the hypotenuse, which is cos pi by 3. So the radius is now cos pi by 3 times cos pi by 6. Well, let's have a look at the next polygon and circle. Here's the 12-sided figure and circle. And so we have to multiply the old radius by cos pi by 12 to get the new radius. The new radius is once again the adjacent side of this right-angled triangle. So can you see what's happening? We got the first new radius by multiplying the length 1 by cos pi by 3. The next by further multiplying by cos pi by 6. And so finally, this radius becomes cos pi by 3, cos pi by 6, cos pi by 12. The general term for a radius comes out to be this product of cosines. Oh, by the way, why is it finally 3 times 2 to the n minus 1 here? Well, you know it's got to be 3 times some power of 2, so just try it for the first circle, n equals 1, as a double check. But that's not a very nice formula to hand over to Phil. We've just got to get rid of that product. Notice, though, that the angles are halving each time, so perhaps it's a good idea to see if a half-angle formula can help. Well, there's a standard one for cos theta and a standard one for sine theta. Now, if you try to use this one to convert the product of cosines, well, you don't get a nicer expression. In fact, because you've got two terms there, it makes things worse. However, if we use this other sine theta formula, then the product of cosines does simplify to a term involving just two sines. Now, you can see this if you start by reordering these terms. That is, just interchange the cos theta over 2 by the sine theta over 2. Now, we can apply the formula again to this term at the end. What am I going to get if I apply the half-angle formula to 2 sine theta over 2? Well, it becomes 4 cos theta over 4 times sine theta over 4. The 4 appears since I started with twice sine theta over 2. Now I've got sine theta expressed as the product of 2 cosines times a sine. Well, can you see where all this is leading? Of course, 4 sine theta over 4 can be rearranged as 8 cos theta over 8 times sine theta over 8. Now I've got the product of these 3 cosines and a sine. A product of cosines is building up with each angle half the previous angle. So if I apply the formula once, then I get as last term 2 sine theta over 2. Applying the formula twice gives me 2 squared times sine theta over 4. Applying it 3 times, I get 2 cubed sine theta over 8. If I apply the formula n times, my last term will be 2 to the n sine theta over 2 to the n. And if we take this last term to the left-hand side, then we get this expression, sine theta over 2 to the n sine theta over 2 to the n, as an alternative to this product of cosines. Now, if we compare that product to the product of cosines that we got from our second problem, then you'll see that they're actually identical if we replace theta over 2 by pi over 3. Well, that's a rather neat trick, and it was actually thought of by Euler over 200 years ago. So thanks to Euler, Phil has this rather neater expression to work with in his problem.
So this, then, is the sequence of radii for the second problem. What's happening as n tends to infinity? The numerator doesn't change, because theta is the fixed angle 2 pi by 3. But look at the denominator. You have a sequence tending to infinity times a sequence which tends to 0. What's the limit going to be? Well, in fact, you can work that out by dividing the denominator by theta, not forgetting to do the same to the numerator. The numerator is still a constant term, sine 2 pi by 3 divided by 2 pi by 3. And the denominator is now nearly in the form of a standard quotient, which is known to tend to 1 as n tends to infinity. It's an important result that, for a null sequence, xn, the sine of xn divided by xn tends to 1 as n tends to infinity. In particular, since theta over 2 to the n is a null sequence, this quotient tends to 1 as n tends to infinity. But these two expressions are actually the same. Multiplying by 2 to the n over theta is the same as dividing by theta over 2 to the n. So the denominator here tends to 1. That means we can find the limit of this sequence. It's sine theta over theta when theta is equal to 2 pi by 3. Well, sine of 2 pi by 3 is equal to root 3 over 2. And so the limit is 3 root 3 over 4 pi. And that's approximately 0.41.
Let's have a look at that sequence again. It certainly appears to tend to a limit, and it does look as if that's a bit less than a half. But you could never have guessed an exact value of 3 root 3 over 4 pi without doing some analysis.
Now it's time to tackle that intriguing third problem. We've seen one example of radii shrinking to 0, and one where they don't. What will happen in this case? Will the circles inside these polygons shrink to 0 or not?
Again, we start with the equilateral triangle and its inscribed circle, which, as before, has radius cos pi by 3. Now, the next polygon is a regular four-sided figure, so its internal angle will be pi by 4. So this right-angled triangle tells us that the new radius will be cos pi by 3 times the cosine of pi by 4. That is, cos pi by 3 times cos pi by 4. Looking at the next polygon will be enough to determine the sequence. This radius, then, is cos pi by 3 times cos pi by 4. So the next radius is cos pi by 3 times cos pi by 4 times cos pi by 5, because we have a regular five-sided polygon. So the general term of the sequence is, again, a product of cosines. Now, I'd really like to simplify this as we did last time, but nobody has found a trick of the kind that Euler used, and a half-angle formula just doesn't work. So Phil will have to work with the product as it is. But at least notice that we have a decreasing sequence of positive terms. That's obvious from the geometry, and you can also see it because the cosines are all positive and less than 1. Well, is that any help?
Earlier in the course, we looked at the monotone convergence theorem. This is how the decreasing version of it was stated in an earlier TV program. That sequence of Allen's is certainly decreasing, and every term is positive, so the sequence is bounded below by 0, and so it must be convergent. But the interesting question is whether it converges to 0 or to some positive number. If we want to show it doesn't converge to 0, we've got to find a strictly positive lower bound.
Well, if you're looking for a positive lower bound, then the thing to do is to work with inequalities for the cosines. And that's where the pre-programmed work with inequalities comes in. You should have found an inequality between the two functions whose graphs I have over here. You can see from the graphs that cos x is greater than or equal to e to the minus x squared in the range mod x less than or equal to 1. But how can this rather strange inequality help us?
Well, if this cosine is greater than this exponential, then a product of these cosines will be greater than a corresponding product of exponentials. And the great thing about a product of exponentials is that it can be written as the exponential of a sum. I've got here the product of cosines from the third problem, and I'm going to try to apply this inequality to each cosine term. Well, each of these angles, pi by 3, pi by 4, pi by 5, and so on, is less than or equal to 1, with the exception of the first one, which is a little greater than 1. But we know that cos pi by 3 is equal to a half. So that product is certainly greater than this product of exponentials. Cos pi by 3 is equal to a half. Cos pi by 4 is greater than or equal to e to the minus pi by 4 all squared. Cos pi by 5 is greater than or equal to e to the minus pi by 5 all squared, and so on. Now, this product of exponentials can be rewritten as the exponential of this sum. There's a common factor of minus pi squared. But then this series should be familiar to you. What is it? Earlier in the course, we found that the infinite series sigma 1 over n squared, starting from n equals 1, is convergent with sum less than 2. So if you lose the first three terms, 1, a half squared, and a third squared, then the sum of the series from a quarter squared on must be less than 1. Knowing that this sum is less than 1 means that this sum in the brackets is less than 1. And that gives this lower bound for the sequence. Why is that? Let's go through the argument in easy stages. The bracket is less than 1. So pi squared times the bracket is less than pi squared. So minus pi squared times the bracket is greater than minus pi squared. And now this holds because e to the x is an increasing function. So it is true to say that a half e to the minus pi squared is a lower bound for the sequence. In fact, e to the minus pi squared is surprisingly small, but it is positive. All the terms of the sequence exceed this number, so the sequence doesn't tend to 0. But because inequalities were introduced, we haven't found a precise value for the limit.
Well, let's look at these pictures again. The circles seem to tend to a limit. In fact, continuing the sequence shows that the limit appears to be about 1/9 of the original radius. With a good computer program, you can get as close as you like to the limit. But you need the power of analysis to be sure that it does converge to a positive limit. Well, there's one more result we're going to prove because actually we glossed over it earlier in the program. But first, let's summarize what we've done in terms of the main analytical results from the block needed to solve each problem. Clearly, the solution to that last problem depended on knowing that the infinite series sigma 1 over n squared is convergent. In the other problems, we first used the fact that the sequence 1 over 2 to the n is a null sequence. That is, it tends to 0 as n tends to infinity. In the second problem, this limit, sine theta over 2 to the n, divided by theta over 2 to the n, tending to 1, played an important role. Remember, that was a particular case of this general result for sequences. Well, Phil's now going to show you how that result is proved.
This is the graph y equals sine x over x, drawn between minus pi by 2 and plus pi by 2. In fact, the domain of that function is the whole real line, except for the value 0. The curve goes on to intersect the x-axis at minus pi and at plus pi. But for values of x near 0, sine x over x gets close to 1. So it does seem that if you have a sequence xn tending to 0, the corresponding sequence sine xn over xn tends to 1. Each term of the sequence xn has its corresponding value sine xn over xn. How do we prove that, though? Well, what we need are some inequalities for sine x over x, and we're going to get those geometrically. Here's a sector of the unit disk with angle x radians. This arc then has length x, and by definition, this vertical has length sine x. The geometry shows that sine x must be less than or equal to x. The inequality is still true if you divide both sides by x, as long as x is greater than 0. In other words, then, sine x over x is less than or equal to 1. So we've proved that sine x over x is less than or equal to 1, at least for positive values of x. Now can we find a function less than or equal to sine x over x? Let's look at the unit disk again. Its circumference, of course, has length 2 pi. And its area equals pi square units. So what's the area of a sector of angle x? It's a fraction of the whole area, which simplifies to a half x square units. Now, if you construct this right-angled triangle, the side opposite angle x has length tan x. And the area of the whole triangle is a half the base times its height. That's a half tan x. Remember, the area of just the sector was a half x, which gives this inequality, or just this. X is less than or equal to tan x. Now, tan x can be expressed in terms of sine x and cos x. For values of x greater than 0 and less than pi by 2, cos x is positive. So you can multiply both sides by cos x over x. On the left, you get just cos x, and on the right, you get sine x over x. So that shows that sine x over x is greater than or equal to cos x for positive values of x less than pi by 2. Of course, all three of these functions are even functions, so the inequalities are true for negative values of x as well. How does this help us to prove that sine xn divided by xn tends to 1, though? Here's a typical term of the sequence xn. And the corresponding height is sine xn over xn. But you can see that that lies above cos xn and below 1. In other words, cos xn is less than or equal to sine xn over xn is less than or equal to 1. And that does it. As xn tends to 0, cos xn tends to 1, because the cosine function is continuous at 0. So, by the squeeze rule for sequences, if xn tends to 0, then sine xn over xn tends to 1 as well.
Well, that's completed the analysis we needed to solve the second problem. All these problems of shrinking polygons are fairly interesting, and we've had to use a good deal of analysis from the block to solve them. But why did Kepler first think of this problem? He tried to explain the motion of the planets using the sequence of polygons in our third problem. That didn't work. Instead, he tried the 5 regular solids with inscribed and circumscribed spheres. He constructed a model like this with a sphere, a cube, a sphere, a tetrahedron, a sphere, a dodecahedron, and so on. Now, this comes very close to explaining the orbits of the 6 planets known to Kepler. One reason why he rejected regular polygons was the simple fact that there are too many of them, infinitely many. But there's another way of looking at our third problem. We can let the polygons expand, starting with a circle, then a triangle around it, then a circumscribed circle, then a square, and so on. What do you think happens to these expanding circles?